Welcome to the Open Systems Media eCast titled Managing Avionics Safety Certification in UAS Platforms. My name is John McHale, Group Editorial Director with Military Embedded Systems and moderator for today's event. Our speakers today are Dr. Robert Dewar, co-founder and president of AdaCore, Gary Gilliland, Technical Marketing Manager for DDCI, and Adrian Whitfield, Industry Offering Manager for IBM Rational. Now for some short housekeeping announcements. The eCast will consume about 35 to 40 minutes, leaving the remaining time for the question and answer session. Before we get going, I want to point out three important buttons on your screen. First, please take note of the Enlarge Slides button. By clicking on this button, you'll be able to view the slides in full screen mode. The second important button is the Forward to a Friend button, which enables you to send an email of request for this event. The third button on your console window allows you to enter questions in real time. We'll do our best to address those questions during the closing Q&A session. If you have a question intended for a specific speaker, please note so at the beginning of your question. Otherwise, I will parse out the questions equally to our speakers. If you have a question pertaining to the eCast operation itself, one of our technicians will respond back to you during the eCast. Please note that as much as we'd like to, we may not get to all of your questions today. In that case, someone may get back to you after the eCast with more information. This eCast will be archived online today and will be available for 1 year. There will also be an MP3 version made available. Now, I'm pleased to turn it over to our first speaker, Dr. Robert Dewar of AdaCore. Robert?
Hello, yes, I see my first slide has appeared. This is Robert Dewar from AdaCore, and perhaps let me make a quick remark first, since my slide says UAV here, and the title of the webinar is UAS. So just to clarify that difference, UAV is the term used to talk about the actual gizmo that's flying around, what people like to popularly call a drone. And UAS embraces the ground station as well. And of course, if we're talking about software considerations, we're always really talking about UASs because we're talking about the combination of software on the ground and in the device itself. So I'm going to make some rather general comments on UAVs and safety and security considerations that I think are important when you're looking at the big picture. The first thing to comment on is that UAVs span a huge range of devices, from tiny toy helicopters with small cameras aboard that are little more than toys, to more serious surveillance devices, serious aerial photography devices, and just to give some sort of idea of real variety, several companies have talked about using UAVs for package delivery. Amazon has talked about that. Google has talked about that. So, and that's an interesting sort of window into the future of a very interesting variety of applications. And then, of course, we have large wing planes flying in commercial airspace and full-blown war machines with missiles, which we're certainly familiar with. Now, given that very wide range of devices, you're going to get a very wide range of regulations. A small surveillance drone doesn't concern those worrying about commercial airspace, but still clearly needs regulation from both a privacy and a safety point of view. On the other hand, large wing drones flying at high altitudes in commercial airspace will certainly and do certainly concern those worried about general aviation safety. And in some cases, a single device may be flying in different airspaces with different regulations. Just one example, you can imagine a package delivery drone, fair-sized gizmo if it's carrying a bunch of packages, traveling in normal airspace, possibly at moderately high speeds, but landing on someone's back lawn in a rural area. That's the sort of picture that Bezo painted of package delivery drones. So when we think about software, we have to address this wide range of concerns. So if we look at safety considerations, that similarly has very wide range of issues that have to be considered. There'll be a wide range of safety considerations Small surveillance drones may not threaten commercial aircraft, but they most certainly can threaten people. I don't know if people saw this story, but recently in Australia, a contestant in a race, in a running race, was taken out by an unauthorized camera drone, hitting him in the face as he neared the finish line. And yeah, I think that's a harbinger of real concerns to come, especially when these devices become more ubiquitous and you have lots of them flying around with the great capability of hitting one another as well as hitting people. On the other hand, large wing drones flying at high altitudes and high speeds most definitely do threaten commercial aircraft and raise the specter of dangerous collisions and accidents. And we haven't seen any serious accidents so far, partly because the use of such drones in commercial space is still very restricted. But we already had a near collision and a real scare. So again, this is something that's going to be much more of a concern as more of these devices are pushed into service. And I think you all are aware that a lot of people are pushing to have more access to airspace for UAVs of all types. Now, to look at security considerations, first of all, just a remark. You can't consider safety these days without considering security. If you have a device whose software can kill someone because of a bug, then it's obviously a possible vector for hacking in to deliberately kill someone. I mean, we've seen that kind of scenario on any number of television series, and it's definitely real. And the wide range of variety of uses means a wide range of security concerns at the sort of beginning end, just corruption or destruction of surveillance records, to if you want to go to the other end, to the full-blown takeover of a military drone. It's interesting that Iran at one point claimed to have achieved this in one case. Facts are far from clear in that particular case, but still, even the fact that they certainly did obtain a drone. Whether they obtained it by hacking the software is unclear. And there certainly have been such phenomena as successful GPS spoofing demonstrated, and that's worrisome because many of these devices rely on integrity of GPS signals. And finally, the very fact of radio control introduces major security headaches. Imagine if someone on a commercial aircraft suggested, well, we'd save a lot of wire if we just used Wi-Fi to have all the various parts of the avionics system communicate with one another. Well, people would really worry about such a proposal because everyone, registers immediately that wireless access means that anyone potentially can have access. Definite concern. Same kind of concerns arise with automobiles. So, what are the software implications? Well, the wide variety of requirements, regulations, and safety security considerations, as well as fundamental uncertainties introduced by remote control. So my view is that the software for UAVs may well end up being considerably more complex than traditional avionics software, which after all has a much more restricted domain. So we're faced with building very sophisticated software systems that must behave absolutely reliably. Now, I'd like to let's turn the attention in broad terms to certification. There's been a lot of discussion on whether UAV software, UAS software, we really should say, should be subject to certification by standards, existing certification standards. Most obviously, if you're talking about flying in commercial space, commercial avionics has to meet the requirements of DO 178B and as time goes on, DO 178C, and it seems a natural minimal requirement for large UAVs flying in commercial airspace to meet the same kind of certification standards. But I'm concerned that it's unlikely to be sufficient. It's well to remember that certification is not a goal in itself. It's a means to an end, the end being reliable, safe software. And DO 178B is a bit of an odd standard in a way. It's basically a testing standard. It guarantees nothing from a formal point of view. You know, if you would ask a formalist, well, I've verified my software, I've certified it to 178B. What statements can I make about the software? About the only statement you can say is that it passes the test that was submitted to it. But still, it's worked amazingly well in the domain in which it's been used, traditional avionics systems. That I am aware, there's never been an accident on a scheduled commercial aircraft that can be tracked back to a software bug. So we tend to trust that standard in practice. But it doesn't guarantee anything, and we should worry about extending that trust, that historical confidence, when we move to new domains. We can't just assume that it will happen to work as well in those new domains, and that's, I think, an important thing to bear in mind. So building complex, reliable software is a daunting task. 178B has been helpful, but hasn't guaranteed freedom from potentially disastrous bugs. We've just been lucky that those bugs haven't killed anyone yet. An important point here, I think, is the safety of drones is going to be under intense scrutiny. Any accidents will have overblown impact. The public has a natural fear of machines that aren't controlled by humans. And there's a similar sort of fear of autonomous cars. So I think we have to absolutely understand that these systems cannot afford accidents. So we need to bring software processes up to a new level of reliability. And I think one important ingredient will be the use of formal methods and formal proof. You can see that we're moving in that direction. For instance, 178C is much more amenable to the use of formal methods, replacing testing in some cases. Formal methods allow proof of properties of programs. We're not really interested in proving entire programs correct, and even if we could, it would be less helpful than you think, because we can easily have errors in specifications, and implementing them faithfully doesn't guarantee freedom from problems. But we can prove important properties like freedom from runtime errors such as overflow and buffer overrun. This is achievable in practice. The entire IFAC's air traffic control system in England is, for example, formally proved to be free of such defects. And we can prove specific security properties. Tokeny is a nice demonstration of that. And new techniques, in particular programming by contract, can be very helpful either in the context of formal proof or outside of it. There are many interesting tools appearing on the market now, and I think one of the jobs of software developers today is to be aware of those tools and look at what can provide help in this goal of reliable software. Static analyzers obviously play an important role, preferably sound ones that really can be in a position to guarantee absence of errors. I mean, I can give some examples from AdaCore, but there are many companies producing interesting tools. We have a static analysis tool called PEER for Ada. There are full-blown proof environments. From AdaCore, we have a Spark 2014, particularly oriented to mixing proof and testing. Coverage analysis tools, which are very useful, independent of certification requirements. And there are specialized tools to handle such tasks as worst-case stack usage, worst-case execution time. Again, I give an example from our own arsenal of GNAT-Stack, which is a static stack use analyzer for Ada programs. But this is just what Ada comes from AdaCore. As I say, there are many vendors offering interesting tools in that area, and I think really making an effort to find out what's available is an important part of the task ahead. So, concluding, UAVs pose a formidable challenge to our ability to generate safe software. I think it's a mistake to think we can solve this merely by requiring some existing standards, though certainly those standards will play a role. And we need to adopt latest state-of-the-art approaches, including the use of formal methods, to address this challenge. So that concludes my presentation. Back to you, John.
Thank you very much, Robert. Excellent presentation as always. Before I turn it over to Gary, just a gentle reminder, if you have questions, please send them in now. We will get to them after our third speaker. And now, it gives me pleasure to turn over to speaker number 2, Gary Gilliland of DDCI. Gary?
Hello and good afternoon. My name is Gary Gilliland. I've been working in this industry in various capabilities for many years, from design to sales to marketing. DDCI as a company is focused on avionics software. We've been in that business for a long time, and all we do is certification of avionics. So it's a single market that we're very proud of our capabilities in. As Robert stated in his presentation, I think it's pretty obvious that the unmanned aircraft system is soon going to be part of our national airspace, and there's just too many areas where it seems there's opportunity to take advantage of this capability. Like you said, even Amazon's talking about delivering packages via that way. The FAA and other worldwide agencies are committed to integrating this capability. The FAA, by the end of September 2015, are going to have, hope to have standards in place to cover a lot of what Robert said as well. It kind of goes into 3 categories. You need to develop standards for operators and pilots of the UAS. What minimum requirements do they need to meet to be able to do this kind of stuff? There's standards for sense and avoid capability, because in reality, there's a lot of cases where UAVs, UASs are autonomous, and they need to make sure they don't run into anything. And then the standards for command and control, which, how do you control the communication between the aircraft and the ground station? To mitigate those and do some of that research, the FAA's put 6 test sites where they're going through a bunch of research to try to figure out, what are all the things that they need to, dig into, and how are they going to accomplish these kind of tasks. So, although I might have a slightly different opinion than Robert on DO 178, I think it's also, an additional opinion would be that it's a process, and as a process, the commercial aircraft industry is feels like it is very reliable. It goes from requirements through specifications, through tests, through verification, and over the years, at least for commercial aircraft, has done a very good job of managing to keep the airways pretty safe. From a commercial UAV standpoint, the software is typically written to just industry standards, which they don't subject these systems to the rigorous requirements that are levied on commercial aircraft via, for hardware via DO 254 or software via 178C. So, even in the military, where UASs have been flying for years, and they even have more strenuous requirements than commercially, over 400 UAVs have crashed in the past 10 years, and those are the most experienced pilots they have. The crash reports blame hardware problems, blame software problems, and pilot error. So it kind of fits in the same 3 categories of what do we have to fix. And I think the point here is that commercial industry standards that exist today are not good enough for these UASs to fly in a national airspace. I put this example up here because I think the question is, what's it going to take? You look at what's in a UAV, and a lot of times we'll look at the small things, the ground stations, but that middle picture is actually a commercial helicopter that was retrofitted for military use. But a lot of the current aircraft systems that are being built today are built to be manned or unmanned. So I think that even from a safety perspective, the pilot is going to have to know what's going on in these systems, and in many cases, the pilot is actually a redundant part of the system. If instrumentation fails in such a manner, he can always correct. Pilots on the ground do not have the same perspective, so they're at a disadvantage. And their perception is only as good as the sensor technology that they have can provide them. So, from a pilot's perspective, he needs to know that his sensor hardware is accurate, the software interpreting the information was designed correctly, and the data links are updating the information timely and in an available manner. I think beyond the requirements, for well-trained pilots, well-designed hardware and software, there are requirements for the ultimate best in sensor technology. Here's just a couple of examples of sensors that are the eyes and ears of pilots in the ground station. Development of these sensors has proven to be the most difficult challenge, as well as have the most immediate value to any of these UAS successes. Manufacturers are relying on the rapid evolution of technology to meet the size, weight, power requirements, while trying to significantly improve the available imagery and situational awareness that these systems have. So with all these requirements, I think it's interesting to look at some of the hardware ideas that are out there and becoming available as well. So I believe that the ARM processor is an ideal solution for this market. Processor technology from ARM has become a game changer for many industries. It delivers the high performance per watt processing, high levels of integration enabled on system-of-a-chip technologies in a very low power device. This combination has been ideal for small form factor systems in avionics, automotive, and medical applications. We're talking to many embedded designers in these markets, and they're looking for ways to take advantage of this technology to enable safety certification via standards such as DO-178C. But, ARM-based solutions can not only reduce the power, but they can easily utilize the integrated peripherals for a safety-certified solution. This combination of attributes makes ARM an optimal solution for the intelligent sensors of a UAS platform. So you got small size, weight, low power, high performance, low cost, high integration of I/O devices, so that can fit in all or to practically any system that needs this kind of hardware. Take that a little bit further. This is just an illustration on the point. This is a block diagram from a Freescale IMX6 integrated system on a chip. You can see it's an ARM Cortex A9. Maybe you can see if it's it might be kind of small. It has a large amount of I/O interfaces, including Ethernet, Bluetooth, CAN, graphics, audio, external memory, and data storage, all built into this system. So it provides that small footprint that a lot of these systems need. There's an importance of using the ARM Cortex A parts because they have an MMU. They're the R and M series parts don't have an MMU, and therefore they have limitations in the ability to provide mixed critical memory partition, virtually addressed machines that are necessary in this highly complex software environment. So, today UASs are not certified really to any standard. So there's going to be some effort required to upgrade these systems to the requirements needed for certification. Right now they have very limited areas where they can fly and do certain specific jobs, but if we're going to turn them loose across the whole airspace, they need to have some certification requirements. And the original intention with UAVs was to have something that's inexpensive. So we want to find the best way to minimize certification cost to do that. But as we've seen this complex environment, there's a value of having this highly integrated devices. But that means there's a lot of I/O, a lot of applications, a lot of interaction in the system. A DO-178 certification of these systems poses a challenge to the system integrator to determine what of these interfaces have to be very high design assurance, and how do you separate those from a low design assurance I/O interfaces. It's important to note that, even if you're designing a high DAL system, that doesn't necessarily mean that every application and I/O interface has to be designed to DAL A requirements. And you really don't want to do this because it increases your cost and risk for certification of your system. With some operating systems that have monolithic kernels, there's no way to separate the drivers from the kernel, which causes device drivers to have to be designed to DAL A. This would be, primarily because the device driver code is in the kernel, and if it fails, it could bring the whole system down. The best way to do this is avoid a fully modular operating system that utilizes the MMU to provide time and space and resource partitioning. So, selecting this type of system can definitely minimize certification impact. Obviously, an operating system that takes advantage of MMU would require a processor with an MMU. As we saw earlier, only certain ARM processors, the Cortex-A series, have an MMU. But with the MMU, an operating system can provide the space partitioning that will separate the applications and drivers in the system such that they cannot adversely affect each other. The architecture also enables reuse and multiple levels of safety certification to run on the same system. In order for your UAS designer to move, to this COTS operating system, they need to make sure that the RTOS they choose has a good certification pedigree as well, and as well as all the functionality that they need and performance. So that's a good lead into DIOS as a solution on the ARM platform. The DIOS operating system has been certified to DO-178 DAL A since 1998. It makes full use of the MMU, time and space partitioning. It's a fully modular design, provides user mode drivers that are separate from the kernel, application, and other drivers. The drivers, applications, and libraries are modular such that they can easily be moved from system to system. A lot of these UAV systems are copies of each other, are adding certain capabilities. So it'd be nice to move a certification, along without having to redo everything in the system. But reuse is not just limited to the drivers. It's also true for the kernel, all the components, and user applications. DIOS also runs in a small footprint and enables, on these SoC platforms, the users to manage how much memory is allocated to the applications through memory pools and cache partitions. One of the keys there is if you're going to go through a certification, it's kind of nice to know that the operating system you choose has been through certification many times. DIOS has had a single line of development since the beginning. Development started at Honeywell in the mid-90s and transitioned to DDCI in 2008. Even the same core engineering team is now at DDCI. The key here is that the engineers know the product and processes used to design and develop code to the DO-178 standard. We've been doing this for a long time with a very good reputation in the industry. So here's a high-level architecture view of DIOS. As I said before, it's fully modular microkernel architecture. The DIOS kernel module is dynamically linked with other components to provide the functionality of the system. A BSP consists of some boot code along with the platform abstraction layer, seen here as the PAL, which provides the interfaces to the platform hardware required for the kernel, which is timers, memory, interrupt controllers, etc. The hardware abstraction layer, HAL, provides CPU family interface to the kernel. So it will, for PowerPC or x86, there may be a difference, but it'll run for the family of PowerPCs. The registry seen there is the personality of the system. It's an input file that defines the resource allocation for all the components in the system. Note that that's all the code that's required to run in kernel space. The rest of the software, including the device drivers, run in user space. With with DIOS, we know that most device drivers execute in user mode rather than kernel mode, as is with the case with a lot of RTOSs. Consequently, the design assurance level of the device driver software only has to be as high as the partition or process that is using that interface. So this is just an example of how a device driver would be architected. The hardware interface library is created to provide a programmatic interface to the hardware, provides the open, close, read, write type functionality. Device driver process here is dynamically linked with the hardware interface library and manages multiple client connections to the I/O interface. The processes that want to use the I/O interface can communicate with the device driver over standard IPC mechanisms, be it shared memory, sockets, etc. And note also that DIOS is architected to handle interrupts, unlike many 178 RTOSs. The interrupt dispatch would be handled by the kernel, but the ISR routine would run in user space along with all the other driver processing. DIOS also has a patented methodology for creating individual memory pools for each application to use that are mapped into separate areas of cache. There's multiple benefits for that. First, it allows you to allocate an application that has very high criticality or extreme timing requirements to an SoC's on-chip SRAM, instead of using the external memory, where you can put your less critical apps. Secondly, it allows the user to partition the cache memory and reduce the interference patterns that applications run into when they're using a shared cache architecture. The separation of these applications in cache has been shown to improve performance and CPU utilization. This technology can reduce the worst-case execution times in complex avionics systems. You know, it's key when you reduce the worst-case execution times, that gives you more schedulable time available for other applications. Basically allows you to have more CPU utilization available for doing real work. This application isolation also reduces the analysis that has to be done for DO-178 and simplifies the verification and certification process. So I think in summary, I think the UAS systems will need, DO-178C certification, along with more requirements, security requirements probably as well. As Robert's presentation pointed out, there's a lot of ideas that have to be done. I think from a hardware perspective, the ARM processors provide an ideal platform to deal with the size, weight, and power issues that UASs run into. And I think I pointed out that DIOS is an ideal architecture for that, to provide those systems what they need in these environments. So there's some contact information if you want to ask me more detailed questions, and I'll turn it over to John for our next speaker.
Thank you, Gary. Well done. And now, before I turn it over to our last speaker, just another gentle reminder to start getting your questions in, because after our next speaker is finished, we'll go right to the Q&A. And now I am pleased to turn it over to Adrian Whitfield of IBM Rational. Adrian?
Thanks very much, John, and thanks, Robert and Gary, for your earlier presentations. Good stuff. So, yes, I'm Adrian Whitfield from IBM. I'm an offering manager within IBM Rational and look after aerospace defense. So let's get started here, get stuck in. So as the other speakers have said, certainly UASs are in the news. There's a lot of buzz around UASs, and we talked about Amazon already, but I'm here living in Seattle, home of Amazon, and I'm patiently awaiting my Amazon deliveries via the Air Prime or the Amazon drone delivery service. Of course, I think we're going to be a few years away from that happening, because government agencies all over the world want to make sure that before they give the green light and allow commercial organizations to use UASs in civilian airspace, they want to make sure that they're going to be operated in a safe and harm-free way It's not going to have an impact on other services, systems or aircraft, including other UASs themselves. So our other speakers have talked already about industry standards and how those can be applied. The fact of the matter is that products are getting more sophisticated. They're getting more smarter. They're more personalised with, individual user needs. And I think unmanned aircraft, unmanned aircraft systems are going to be no different here. And all this product innovation is great, but the problem is that this is all adding more and more burden on engineers and the people responsible for developing the UASs. We as engineers need to do more. We've got less resources available. We need to make sure that these products we're developing really meet customer needs, the market needs, the business needs, and of course any regulatory needs, such as the FAA order 8130, which is all about applying airworthiness certification to UASs. An airworthiness certification is all about proving to the FAA that your UAS is safe to operate in all conditions and has been designed with engineering rigor. Now, UASs are heterogeneous systems. They're made up of both flight hardware, software, ground stations. So hardware and software aviation standards like DO-178 and DO-254 can be applied to show evidence that these software and hardware parts have been developed using known processes with the right checks and balances in place and the right validation and verification activities in place. Now, as our other speakers have said, there may be extensions that are required for these standards, DO-178 and DO-254. But the point is, regardless of what the underlying standards will be, whether or not we choose to use them as is or they're extended to support the application, the UAS application, all these standards increase project cost. If we take a look at DO-178B as an example, because DO-178B has been around for many years, so we've got some good historical data. These metrics came from one of our partners at IBM that's been working with many customers developing avionics equipment over the years and have gone through many certification exercises. But if you consider a baseline project with a solid process in place and an experienced team, typically we've found that DO-178B will add between 25 to 40% cost to the development on the first iteration. And that's with a solid, experienced team in place with good processes in place. So you're looking at anywhere between 25 and 40% cost increase. And then, as you go through these iterations, again, you can often reduce those costs because you can reuse IP, you can reuse software, process, and so on. But in many cases, we've found that, in fact, a first-round project will see costs anywhere between 60 to 100% cost of the base development costs. And that's due to overall inefficiencies in their design. So when I say inefficiencies, what am I talking about? Well, I've listed a few out on the slide, but it's things like, for example, inadequate formal plans or not following them. A common inefficiency is not having good plans and then subsequently following those not very good plans as well. So that's not good. Inadequate level of detail and increasing complexity. As we've talked about, these new UASs are going to be very complex. Perhaps we're going to add new levels of automation to them. It's going to be a complex and very sophisticated system. Inadequate and non-automated requirements management and traceability management. We can't have any ambiguity in our requirements, and we need to ensure that we've got good traceability in place. Perhaps it's improper tool qualification as well. We're either doing too much or too little. We're spending or taking up valuable engineering cycles doing tool qualification when perhaps the tool doesn't need to be qualified. And then weak process and checklist management as well. So what can we do to help developers of unmanned aircraft systems? Well, we believe that UAS development organizations need to focus on three principal areas to be successful. We need to have processes and plans in place. We need to make sure that our engineers are following those plans and there's accountability in place. We need to do it in an efficient way, a collaborative way. We don't want to waste valuable engineering time looking for information. We also need a way to deal with complexity and describe and understand requirements, specifications, design, and higher levels of abstraction in a way that isn't ambiguous and is functionally correct and can be properly tested. And then finally, we need a way to organize our requirements efficiently, have links, have traceability in place, so that if something changes later, we can quickly understand the impact that has on the rest of the design. So each of these needs can be mapped to a solution: process enactment with collaboration, model-based design, and requirements engineering. And these three in turn can be addressed through a best-of-breed tools from IBM. Rational team concert to ensure plans are properly followed with process enactment, Rhapsody for your modeling needs, and DAWS for your requirements engineering. So by focusing on these areas, we can help reduce costs associated with having to comply to industry standards often recommended for UAS development. So let me just quickly go through some of these points here. So all products begin with requirements, and UAS development will be no different. And if we're going to have any chance of building a successful UAS that meets the market needs, satisfies industry regulatory needs, we're going to need to employ requirements management. And requirements management is all about putting formality in place around your requirements engineering activities. So with IBM being a leader in requirements management over the years and working with customers, we've recognized that to be successful in requirements management, there's a number of key capabilities you need. Granularity. Can I get sufficient granularity, beg your pardon, so I can trace requirements to another requirement? Document-to-document type of traceability is no longer sufficient given the complexity of the products and the UASs in place. Are there attributes that I can use to tag to capture additional properties and provide some more detail about my requirements so they're easier to consume? I need to organize my requirements as well into a hierarchical structure, which is going to lead to much better traceability in the long run. I need to be concerned with history and security as well. Who sees what information and who edits what information? Reporting is key as well. And then, of course, collaboration. We need to collaborate efficiently so we can get our UAS out the door on time. But we also need to collaborate in a way that ensures that that valuable feedback we get during design reviews or audits isn't lost in a separate email discussion or meeting minutes stored in some filing cabinet. The information is always accessible within the requirements management tool, like it is with IBM Rational DAWS. So let's talk about one of the other areas that I talked about that we're going to focus on, and that's the modeling domain. Modeling and model-based design allows engineers to understand better complexity. And it should be noted that modeling is also recommended in standards like ARP 4754 that can be applied to UAS, also revisions to DO 178 with DO 178C, also calls out use of modeling during the design process. But how does models help you deal with complexity? Well, through the use of models, we're able to graphically represent requirements using modeling notations like the OMG, Object Management Group's Unified Modeling Language, UML, or the Systems Modeling Language, the SysML. And you use graphics as a way of describing the system. Graphics are much easier to digest than text. But it's also the ability to be able to decompose and break down functionality into smaller pieces, because smaller pieces are much easier to understand and be able to consume. And then, of course, the other aspect is bringing those graphical views to life through the use of simulation and execution. We can animate the diagrams so we can see exactly what functional mode we're in or what message has been sent between different parts of our architecture of our UAS. And this can be done in the modeling environment we use to build the model, or we can actually do it on the hardware itself through the use of hardware in the loop simulation. We can even build automatically test cases from the model and then actually run them on the real hardware. So it's a great way to understand complexity and properly describe requirements and specifications as well. And then finally, the other domain is a product called Rational Team Concepts. What's all of that about? Well, we talked earlier about problems that projects often come and face with being able to follow plans and processes when it comes to complying with standards like DO 178. And Rational Team Concept is all about providing a platform to allow engineers to work and collaborate together in a way that's very efficient and disciplined. It can ensure that processes and plans that are defined are actually followed and repeatable by all the different stakeholders. We actually call that process enactment. So that means that the quality assurance departments, assessors, project managers, or anyone else, any other stakeholder for that matter, has visibility into the project. Everybody knows what they're working on, who's working on what, how much has been completed, what the next steps are. So it ensures that that information is readily accessible to all the different stakeholders in the project. And it's great if you've got to prep for a regulatory audit, for example. And Rational Team Concept works with rational requirements management solutions that I talked about earlier, and the modeling solutions as well. And we do that through our JAS technology. And JAS utilizes open standards that allows this tool interoperability and collaboration to take place. And the fact that it is an open standard means that not just IBM can use it, but also other tool vendors as well that would like to participate in this. So when it comes to having to comply to standards, we IBM that is, want to give our customers as much help as possible here. So that's why we've got a number of specific industry solutions that are available. Specifically, I mean, as an example, DO 178B and C, we have custom templates for doors, for example. We have qualification kits for Rhapsody and our Rhapsody kit for DO 178B and C. And then finally, we've got some specific process help as well that provides a number of assets that allows projects to comply to industry standards like DO 178B and C. It explains how you can use our rational products to help support meeting the objectives that are defined in the standard. And then this guidance can then be enacted inside a Rational Team Concept to ensure that it's being enforced and properly followed. So what I'm going to do now is I'm just going to finish up with a quick success story. Jet Propulsion Laboratory, JPL, they're a federally funded research and development facility. They're based in California, and they're managed by Caltech and NASA. And JPL conducts robotic space exploration missions in the fields of planetary exploration, earth science, and astrophysics. Now, in 1996, JPL adopted IBM DOORS software, and it's become the organization's institutional requirements management tool for large projects across multiple levels within the organization. And the tool was used to support many of the Mars missions, including the recent Curiosity rover mission. So DOORS helped JPL manage the complex relationships between the 16,000 requirements and the verification activities for those requirements. And, you know, those relationships could be quite complex with many-to-many type complex relationships. Now, before JPL began using DOORS, it relied on a verification matrix in a spreadsheet to perform all the V&V activities. But this approach made it very difficult to share information and keep control of version control and track changes and so on. And there was no way to link requirements to the related verification activities as well. So with DOORS, JPL staff were able to collaborate and link relevant activities and information, helping enable much greater traceability, efficiency, and reduce errors in the long run. So JPL estimates that DOORS saved the work of at least one full-time employee in their verification and validation activities. So let me hand you back to John now for any questions.
Thank you very much, Adrian. Speaking of those questions, let's get right to them. Our first question from the audience. With respect to DO 178B or C, it only seeks to verify that requirements have been met It doesn't validate requirements. The system requirements process should identify, validate, and flow any software requirements to the software process. Have you considered SAE ARP 4754A or the new security certification process guidance RTCA DO 362A or DO 355 and DO 356? Who would like to take that first? This came in during Robert's presentation, so I guess either Robert or Carrie. Who would like to field that?
Well, I guess I can take it. I mean, I don't know I can speak very specifically to those standards, but just in general, it's certainly true that success in this area comes from end-to-end attention to all aspects of the process. And most certainly, you know, as previous speakers have mentioned, concentrating on developing correct requirements and making sure those requirements are really what need to be met, crucial, because otherwise you end up implementing something you don't want in the first place, and that happens all the time in practice. So I guess that would be my comments there.
Anybody else want to take a stab? Go ahead. Yeah, go ahead.
It's Adrian here. Hi. Yeah, I mean, I actually agree with the gentleman that was asking the question. I absolutely believe that other standards out there do apply for UAS development, such as ARP 4754, which is all around the sort of system engineering activities, absolutely required and needed. It's all about engineering rigor. You know, you've got to show that you are following the right processes, the right practices, and all the checks and balances are there. You know, that's all part of the certification activities. So yeah, absolutely essential.
Okay. Next question from the audience. Am I correct to state that even if we would have reliable means, in other words, a follow-up of DO 178 formal methods, to make sure that software implements correctly the requirements, a bigger challenge for UAVs is to get an agreed set of requirements they have to implement? There's a question in there. It's not assigned. Who would like it?
This is Gary. I'll take that one. I think that is the biggest challenge. I think even the statement by the FAA is that's their biggest challenge. They've agreed to try to come up with requirements by the end of September 2015, when in reality, as part of their next gen plan, they were trying to figure this out, 4 or 5 years ago, and they still have struggled a lot because, although they are airborne systems, they have some capability for that. There's a whole lot more to it than just a standard aircraft with a pilot.
Okay. Anybody else like to take that? Nobody? Okay. Next question from the audience. For Gary. Gary, what are the limits on sharing these slides, given the confidential? We'll be sharing slides. The slides that we have will be available for download if you're a participant of the webcast.
Yeah, and I left, our standard slide set has confidential and proprietary, so I left those on there. I don't think that there's any slides there that need to be worried about in that respect.
Okay. Next question is also for Gary, I'm guessing, because they're asking, is DO certified to DP 178C requirements and required supplements?
I think that means DO, but we've transitioned all of our processes and procedures over to the DO 178C standard, and we are currently in process going through verification of all that with the customer. Certification of a subsystem is based on a customer going through their certification, so we're reliant on them to get the complete system through. But everything we do and we develop to the 178C standard.
Okay. Looks like the next one is for you as well. What are the examples of current avionics products applications which have used DO and are certified on the commercial aircraft?
There's a lot of different systems, air data computers, inertial reference units, cockpit displays and video, data recorders, weather radar, TCAS, flight controls, flight instrumentation, flight management, and they're on, various different large Airbus, Boeing, and business jets of Embraer, Gulfstream, those kind of things.
Okay. Next question is for Adrian. We have been considering doors for our next UAS project. Is there anywhere we could try it out before we commit to a purchase?
Yeah, absolutely. The best place to go is to go to the website doorsng.com, and there it's all hosted in the cloud online, and we've got some example projects as well. And there you can actually go in, and go at it and really take it for a spin without having any hesitation to worry about committing to anything. So yeah.
Okay. Next question is for Robert. Will the use of new techniques mean significant retraining of existing programmers?
Well, I think the interesting thing there is it's not so much learning new languages, learning new tools. It's more along what Adrian said of building a discipline to do things efficiently and to learn the whole attitude towards the care and focus of engineering that's required to do a best possible job at every stage. And that means learning some new things for many programmers, there's no question. But as I say, I don't think it depends so much on specific new techniques, specific new tools. It's more a matter of generally learning what it takes to have a rigorous, high-quality view of every stage of the procedure.
Okay. Next question is for Robert as well. Isn't the adoption of formal methods likely to significantly increase development cost?
Well, that's a very common question, and I guess there are two answers that can be made to that. First of all, you have to ask what the cost of failure is, and often the cost of failure, especially late on, is huge. I mean, I'm sure if Boeing had figured out a way in advance to avoid the problem with the batteries on the 787, it would have saved them a really incalculable amount of money and bad press. And I think the UAV situation is going to be similar. Errors are going to be very expensive. So, yes, you may end up spending more time up front, but as Adrian points out, that can be minimized, the amount of effort you spend up front, by bringing sufficient discipline to the whole process. So I think the cost is less of an issue than looms in people's minds in practice.
Okay, thank you, Robert. Next question is for Gary. Which ARM processors do you currently support?
Right. So currently, as I discussed in the presentation, we support the ARMs with the MMU technology, which is typically the A8, A9 technology currently. There's also the Altera hardcore IP for the Cortex A9. Since we're supporting an SoC model, there's a lot of these, such as the Xilinx and others, that we would have the core support as well. It would just need minor tweaking for device interfaces on whatever platform they would be on.
Okay. Next question is for Adrian. We're looking at using modeling for our next project. Typically, what steps do you recommend to start that journey? My concern is that there is too long a learning curve for engineers to adopt model-based design.
Yeah, I mean we get that quite a lot. I mean, that's a common problem. A tool itself doesn't necessarily make everything right. It's about picking a language, a description language, whether it's UML or SysML perhaps or something else. It's about picking a tool, and then it's about picking a process, and following that process as well. So the one thing that we offer is we actually provide a dedicated system and software engineering handbook that goes along with the modeling tool. It's called Harmony, and you can download it absolutely for free from our website. All you need to do is just go along to www.ibm.com/support and search for the IBM Rational process Harmony textbook, and there you'll be able to download it.
Okay, thank you, Adrian. Next question is not assigned. Are these systems compatible with AI integrated systems? Anyone want to take that? Anyone? Going once? Twice? I think our panel will pass on that question. Maybe if you could hash it out a little bit more, they will get back to you perhaps after the webcast. Next question from the audience. This one is for Gary. Does a UAS require an operating system to be certified?
No, and I guess, the implication is that we were saying that, and in current UASs, there's a lot of systems out there that don't have operating systems. I think the point would be that as software gets more and more complex and you have more and more applications, processes running, and you will have the ability to do multi-level certification. Some systems are very important, some systems are not very important. Then an operating system makes that much more easy to be put in a certified environment. So operating systems give you flexibility. That flexibility enables certification. And so that's why, an operating system like TIOS is a good idea in a complex system.
Okay. And the last question we have time for is for Adrian. The DO-178 process libraries you referred to look interesting. Are they available somewhere to take a look at?
Yeah, it's the same. If you just go along to ibm.com/support and just search for solution process assets, you'll be able to find them, and you'll be able to download them and check them out.
All right, and that brings us right up to our time limit for today. I'd like to thank Dr. Robert Duar, Gary Gilliland, and Adrian Whitfield for speaking today, and AdaCorp, DDCI, and IBM Rational for sponsoring the event. The CCAST will be archived online today and will be available for 1 year. An MP3 version will also be made available. Thank you all for attending. I look forward to seeing you on future Open Systems Media eCast. Goodbye.